Hey everyone, in this video we're going to learn about exponential functions. To start, we're going to look at an example that exhibits exponential growth so we can understand what type of situations exponential functions would be useful for. There are currently 5 lionfish around a coral reef. Each week, the number of lionfish around the coral reef doubles. Fill in the chart to find out how many lionfish there will be in 4 weeks from now. So we see the table of values. The top row is the number of weeks. The bottom row is the number of lionfish. Currently 5 lionfish around the coral reef, so 0 weeks. No time has passed. We have 5 lionfish initially. Then the number of lionfish around the reef doubles each week. So after week 1, we'll have 10 lionfish. After week 2, 20. After week 3, 40. After week 4, 80. So we can see the doubling in the values that we filled in. Notice that we start relatively small, only 5 lionfish, and very quickly we build up to 80 lionfish. So this is one of the properties of exponential growth, where things start small, and in this case they're doubling, so they grow very quickly. We'll also look at exponential decay, which is going to be things getting smaller very quickly. So now that we have this table of values filled in, we're going to answer a few questions based off this table. What operation are we using to find the number of lionfish from one week to the next? So we went from 5 to 10, 10 to 20, 20 to 40, and each time we multiplied. So the operation is multiplication. And what value did we multiply? We multiplied by 2. Because the value doubled each week, right? 5 times 2 is 10, 10 times 2 is 20. If 4 weeks have gone by, how many times do we need to multiply the initial amount by 2? So if I wrote this out, the initial amount is 5, and that was 0 weeks. After week 1, we multiplied by 2. After week 2, we multiplied by 2 again. Week 3, week 4. So we wound up multiplying by 2 4 times. Now, can we write this in a more compact way? 5 times 2 times 2 times 2 times 2. Well, what if we wrote it as 5 times 2 to the 4th? Right? 2 times 2 times 2 times 2 is equivalent to 2 to the 4th. So we can write it with an exponent, which leads perfectly into the next question. What mathematical operation can we use to show repeated multiplication by the same value? And just as we did in the example above, we represented 2 times 2 times 2 times 2 as 2 to the 4th with an exponent. So exponents are the mathematical operation that we can use to represent repeated multiplication by the same value. So notice we're building into the idea of an exponential function. Right now we just have an expression that we use an exponent in. Now how can we take that idea and turn it into a function? If y is the number of lionfish after x weeks, write a function that can be used to model this situation. So again, let's start with an expression. So initial amount was 5, and we're multiplying by 2 each week. So times 2, times 2, times 2. And now we're multiplying it for x weeks. So I'm just going to include 3 dots. We don't really know what x is, but we can continue out this multiplication as much as we need. And I'll indicate, right, we're doing that for x weeks. Well, if we multiply 2 for 3 weeks, it would be 2 to the 3rd. Multiply 2 for 4 weeks, 2 times 2 times 2 times 2, that was 2 to the 4th. So what if we do it for x weeks? What would that become? That would be 2 to the x. And that's the key in creating this function. So y is going to be equal to 5, which is the initial amount, times 2 to the x. And that indicates that we're multiplying 2 by however many weeks we're letting the growth happen for. So if we want to know how many lionfish there are after 10 weeks, well then x is going to be 10, because we'd multiply 2 times 2 times 2 all the way out 10 times. So if we plug in 0 for x in our function, what value do we get for y, and what does this value represent in the context of this problem? Okay, so let's plug in 0 for x. So this brings back some exponent properties. So 2 to the 0, if we evaluate that, it will be 1. So we have 5 times 1, which is equal to 5. So what does this value represent in the context of this problem? Well, that's how many lionfish we started with. Okay, so it represents the initial number of lionfish. Hey, and the reason it does is, what does 0 represent, right? We plug 0 in for x, so 0 is the number of weeks. So before any time has passed, we're starting with 5 lionfish, and then we go from there. Okay, so in the context of this problem, 5 represents the initial number of lionfish. Use the function to determine the number of lionfish around the coral reef after 10 weeks. Okay, so we're going to plug 10 in for x. 5 times, that looks like a 1. Let's fix that. 5 times 2 to the 10th. Now we can do this by hand, but if we use a calculator, it might make our life a little bit easier. So I'll pull up my graphing calculator. Okay, so we're going to do 5 times, in parentheses, 2. Now we need an exponent. So look at this key right here. It looks like an arrow up key. You click that, and that's going to give us an exponent. So to the 10th, and hit enter. So 5,120. So our answer, 5,120 lionfish. So in general, an exponential function is of the form y equals a times b to the x, where a and b are constants, and a is not equal to 0, b is greater than 0, and b is not equal to 1. We call b the base of the exponential function. So the term base is one that you'll hear frequently when working with exponential functions. Now there's a lot to take in on this slide, even though it might not seem that way. So let's start at the equation. Y equals a times b to the x. So b is our base. Our input, which is indicated by the variable x, is up at the exponent. Okay, that's why it's called an exponential function. We're plugging our inputs into the exponent. And then a is the coefficient. Now in our definition, it says that a can't be equal to 0. Well, if a was 0, we'd have 0 times some value. Well, 0 times anything is 0. Y equals 0 is the graph of a horizontal line. And that's not exponential. Right? Graph of a horizontal line, that's just staying the same the whole time. Okay, so that's why the coefficient can't be 0. Now we'll skip over the second piece and look at why the base can't be 1. Well, if the base was 1, we'd have 1 to the second, 1 to the fifth, 1 to the negative third power. All of those examples I just listed would all give us out 1. So no matter what our exponent is, 1 to that exponent is 1, times a, the coefficient, would be a. Maybe the coefficient is 4, maybe it's negative 3, doesn't matter, but we'd have y equals a, which again is the graph of a horizontal line. And for the same reason that the coefficient can't be 0, the base can't be 1 because a horizontal line is not an exponential function. Okay, so that's two pieces. Now, why does the base have to be greater than 0? Why does the base have to be positive? So let's think if the base was negative. Let's say negative 2. So negative 2, let's suppose, so negative 2 to the first, well, that would be negative 2. Negative 2 to the second, well, that would be positive 4. And as we continued our list, we go negative, positive, negative, positive. Well, think about the situation that we use an exponential function for in the beginning of this video, right? The lionfish population. Would it make sense to go 5, negative 10, positive 20, negative 40. Right? There wouldn't be many situations that we could create where that would make sense. Okay, so that's out, and we're going to restrict the base to be strictly positive. Can't be 0 for the same reason the coefficient can't be 0. Now, one last thing I want to look at before moving on is comparing two functions to one another. So we have y equals x squared and y equals 2 to the x. So y equals x squared, we should be able to identify that as a quadratic function. Graph was a parabola, we did some factoring and solving, but there is an exponent there. So a lot of times students mistakenly call this an exponential function. Whereas if we look at y equals 2 to the x, that is the exponential function. Well, what's the difference between the two? Well, here, the exponent is always 2. That doesn't change. It's the base that's changing. We're plugging in for x. So maybe we have negative 1 quantity squared, or 15 squared, as we plug into this function. But we're always squaring the value we plug in. In comparison to our exponential function, the base is always 2. The base never changes. The exponent is what's changing. We're going to have 2 to the 4th power, or 2 to the negative 1st power. But the base is always 2. It's the exponent that we're plugging into. So it's an important difference between a function such as a quadratic and an exponential. They look similar. I use the same values, x and y, the same number as 2. Right here I could use y equals x cubed. I could have used a cubic, and then I could have made this y equals 3 to the x. But we have to be able to discern between an exponential function and a function like a quadratic. Okay, so now that we've established the main ideas of an exponential function, let's apply them in some problems. The population of Amur leopards is modeled by the function f of x equals 60 times 1/2 to the x, where x represents the number of years. So is the function exponential? So to answer that question, look at the variable. In this case, it's x, and that's in the exponent of the function. So yes, x is an exponent. What is the initial population? Well, if x represents the number of years, initial population is when x equals 0. So we're trying to evaluate f of 0, which is 60 times 1/2 to the 0. Properties of exponents again, 1/2 to the 0 is 1. So 60 times 1 is 60 leopards. And what is the population after 2 years? Okay, so there we're looking for f of 2. So that's 60 times 1/2 squared. So we could use our calculator, but in this case I think we can do this by hand. So that's going to be 60 times 1/4, and that's going to be 15 leopards. And the last question, what is the base of the function? Well, the base is the value that we're raising to the exponent, so in this case, the base is 1/2. So this is an example of exponential decay. We're getting smaller values exponentially, right? We started with 60 leopards, and then we're halving them each time. So after 1 year, we'd have 30. After 2, we could see we have 15, and that pattern would continue on. Write an exponential function to represent each of the following table of values. So as a reminder, exponential function is y equals a times b to the x. Okay, so we need to figure out what the initial amount is and what the base is. So let's start by identifying the base. So in our first table of values, x is the top row, y is the bottom row. So our base is what we're multiplying to get from 1 to the next. So what do we have to multiply to get from 1 to 3? So that would be times 3. What about, I'll use an x instead of a dot. And what about from 3 to 9? Times 3. What about from 9 to 27? times 3. So our base is 3 to the x. And then we need that initial amount. If we plug x equals 0 in, 3 to the 0 is 1. So what do we have to multiply to get 1? Well, that means our coefficient would be 1, and we have y equals. So again, if you're not sure where I got that part from, right, we know when x is 0, y is 1, so I can plug it in essentially. 1 equals a times 3 to the 0 power. So 1 equals a times 1, so 1 equals a. And we can solve that out each time if we need. Next table of values, so from 12 to 2, that's times 1/6. And then from 2 to 1/3, that's also times 1/6. From 1/3 to 1/18, that's also times 1/6. So the base is 1/6 to the x. And then what's our initial amount? What's our coefficient? Well, when x equals 0, y is 12. So we have y equals 12 times 1/6 to the x. Again, we can show this workout if we wanted. Same directions, new table. Let's start by identifying the base first. So -7 to -28. So that's times 4. -28 to -112, that's times 4. And -112 to -448, that's times 4. So the base is the value we're multiplying by each time. So we have 4 to the x. And when x is 0, our y value is -7. So our coefficient is -7. Y equals -7 times 4 to the x. For this one, I'll show the workout again for the -7. So -7 equals a times 4 to the 0. Right? -7 is our y, 0 is our x. So -7 equals a times 1. -7 equals a. Our next table, from 50 to 10, so that's times 1/5. From 10 to 2, that's times 1/5. From 2 to 2/5, that's times 1/5. So our base is 1/5. So we have 1/5 to the x. When x is 0, y is 2. So if we showed our work, we'd find that the coefficient is 2. So we have y equals 2 times 1/5 to the x. Write the exponential function that represents each of the following situations. The number of people infected by a virus triples every day. So we're going to assume the virus started with infecting one person. Okay, so our initial amount is 1. And then our base, we're tripling every day. So we'd be multiplying by 3 over and over and over again, repeated multiplication by 3. So that's why it's an exponential function. And we'll write f of x equals 1 times 3, right? Because repeated multiplication of 3 to the x. And we need a let statement. We're going to let x equal the number of days. And then a scientist has 64 grams of a radioactive isotope. Every hour, the amount of radioactive isotope is halved. Okay, so what would we be multiplying by each time? We'd be multiplying by 1/2. Okay, so the base of our function is 1/2. Our initial amount, when x equals 0, we have 64 grams. So 64 is our coefficient. So f of x equals 64 times 1/2 to the x. And we're going to let x be equal to, well, every hour. So x is the number of hours. So the reason it's so important to define our variable in these problems is because we should notice the time unit might change. In the last example, it was days. Here, it's hours. Right? We can use our variable for any time interval, time unit. We just have to make sure we specify what it is. Are we working in days? Are we working in weeks, months, years, minutes, hours? So really important that we define our variable when creating an exponential function. So we covered a lot. Okay, but the main idea is what is an exponential function? That y equals a times b to the x, and it's a way to write a function that models repeated multiplication. Right? If we're multiplying by 3 each day, if we're multiplying by 1/2 every hour, repeated multiplication creates an exponential function. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.